Welcome. So this question says, using the method of calculus that was shown in physics class, show that the moment of inertia of a solid cylinder about the axis through its circular center is half mr squared. So let's visualize first of all. There's the front face of my solid cylinder, and I'm going to indicate the depth of the solid cylinder. The cylinder has a radius of r, big R, and a mass of m, and a thickness, we'll call that thickness T. And I want to find its moment of inertia about its circular symmetrical point on the front surface. As an axis, basically, pinning this thing so it spins around the axis. Okay, so I need to have an expression for moment of inertia, and my moment of inertia is equal to the integral of r squared dm. Okay, I have no idea how to do that. I don't know how to integrate r squared with respect to dm. What I need to do is I need to convert this dm into some function which contains dr, so I can integrate my function of r. So I'm going to say, well, okay, let's picture a slice. Well, a slice in this case would be more accurately called a sleeve. It's basically a narrow sleeve of this material, and this sleeve has a radius at r, and it has a sleeve thickness of dr. And if you like, I can say, well, it's going to have a mass of dm, a little bit of mass. So let's first of all use our physics to develop an expression for dm. Well, dm will equal the volume density of the material times the sleeve volume. That seems pretty straightforward. Well, dm will equal big M, the mass of the entire cylinder, over the volume of the entire cylinder, which is pi times big R squared. That's the front face times T. And the sleeve volume, well, to get the sleeve volume, I'm going to draw a diagram and then I'm going to erase it. So here's my sleeve. It looks like that, and then it's got the same depth as the rest of the cylinder. So it looks like that, if you like. And I'm going to cut it and unfold it so it's a nice geometrical shape. It's three-dimensional, so we'll show it as having a certain thickness. So it turns out that when I take a circle like that and I want to unfold it, this is the circumference, which is 2 pi times r, and in this case it's the little r, it's the radius of the sleeve, and then this dimension here, this is the thickness of how far the sleeve goes into the page, and then, if you like, the cross-hatched surface on this diagram is the cross-hatched surface here, and that's dr from there to there. Well, it's a three-dimensional shape, isn't it? So that means that my three-dimensional shape is going to be having a volume of 2 pi r, 2 pi little r, times t times dr. Okay? So I'm going to erase this diagram now because I no longer need it and I do need the space. So just let's have one more look. I took the sleeve and I cut it along a seam and I unrolled it because I want to find the volume of the sleeve. And the width is 2 pi r because it's circumference. And the height is t because it's the thickness of the cylinder. And if you like, this front edge is dr high because it's the actual little width of my sleeve. So that's where those terms come from. Let me just recapture this space now. If I was doing this, in a test, I would leave the diagram in. I'd give you more space if this was a test question. And then let's simplify where I can. Well, the thing that simplifies is that the pi's go away and the t's go away, but the rest stays. So I have the mass of the entire object 2 times the mass of the entire object times the radius of the sleeve dr over the radius of the cylinder squared. So let's carve up some space here. Here's my diagram. Here's my conversion from dm to dr. And now let's apply this change over here. So I'm going to say I is equal to, well, let's do this, the integral of r squared, and instead of dm, I'm going to put down 2m r dr over big R squared. So let's continue and pull all the constants out. Well, the 2 comes out and the big M comes out and the R squared comes out because they're all constants. And that leaves the integral, well, I have a little r squared and a little r, so that would be little r cubed dr. So I is equal to 2m over big R squared times r, little r to the 4th over 4. And I need to do my limits. The smallest value of the little r that I will consider is when the sleeve is right on the axis of rotation. And for that point, the little r would be 0. And the biggest value that little r can have is when the sleeve is on the very edge of the cylinder, and that has a radius of big R. So I is equal to 2m over big R squared, big R to the 4th over 4 minus 0 to the 4th over 4. So I is equal to 2m over R squared times R to the 4th over 4, which equals 1/2 m R squared. And that's the expression that we had to derive, and there it is. If I was given numerical values, I would substitute in for these numerical values. Now, frankly, in many questions, you don't have to derive this expression. So you'd simply commit to memory that the moment of inertia of a solid cylinder is a half mr squared. But this is a question where I'm specifically asking you to prove this expression using the method of calculus as shown in physics class. And what I mean by that is sometimes if you look in the calculus books, they'll do something similar. But what they do is they kind of jump in and they don't refer it back to the basic physics in the way that I'd like you to do it. So I think it's very important that you recognize that, that dm is actually the mass of that sleeve, and the mass of this sleeve can be expressed from basic principles as a volume density over a sleeve volume, and then you logically let the physics take you and give you an alternative expression for dm, which is dependent upon dr. Then you substitute in and then you do the calculus bit. The calculus bit is important, but it's how you get to the calculus bit that I think is the real physics insight, and that's what I'd like to see. So there we have it.